Hi everyone, welcome to the Fortify Tech Talk on Fluxprint. My name is Josh Martin, CEO and co-founder of Fortify, and today I am excited to share with you a little bit more detail on one of our core pieces of IP at Fortify, Fluxprint, which allows for better material properties using aligned composites. And just as a reminder, Fortify has recently launched a series of printers, software, and materials that are targeted towards high performance applications in the polymer matrix composite space. And the key thesis here at Fortify is that additive manufacturing is only going to go so far with pure polymer chemistry alone. And if you look at how polymer matrix composites have revolutionized other manufacturing industries, such as injection molding, there's plenty of room for opportunity to combine the high performance of fiber-filled polymer matrices with the high fidelity and throughput of additive manufacturing. Now, before we dive into things, I'd like to take a few moments to talk about some of the biocomposites that have inspired us at Fortify. And within biology, there are plenty of examples of composites that are actually capable of producing pretty remarkable mechanical properties. Bamboo, for example, despite being made out of very simple building blocks, is able to achieve a strength higher than steel at 10% the weight. And this is primarily due to what's called hierarchical design, or being able to control the precise ordering of material throughout many length scales. And that's something that additive manufacturing can really enable using modern synthetic and man-made materials. And one other example we'll discuss today is referred to as nacre, which is primarily ceramic, around 95% by weight, but it's also very tough. So you have something that's strong, stiff, and tough, which are usually mutually exclusive. And at Fortify, we are taking a page out of nature's playbook and applying them to 3D printed composites. And if you look at engineering materials today, there's pretty high fidelity at the higher length scales, at the longer length scales. And you can see a few areas where traditional manufacturing really shines in terms of controlling for what's effectively particle alignment or material orientation. And again, Fortify here is really driving manufacturing techniques down another order of magnitude through the use of Fluxprint, which we're excited to share. So when it comes to fiber orientation, there are a number of different methods. The most ubiquitous by far is the use of shear. And in 3D printing, this is apparent in any extrusion-based FFF or direct write technique, where you're essentially squeezing material out of a nozzle and particles are orienting in the direction of material flow. This is also really common in injection molding of, let's say, a glass-filled nylon, where your tool geometry and the inlet is actually going to dictate how fibers orient as it fills the mold. And what's interesting is that the fiber alignment really matters when it comes to strength. In fact, if your fibers are not oriented in the right way, you could see a 25% tensile strength compared to having those fibers aligned in the direction of load. And so it's a huge drop. And with these types of processes, you're inherently limited to the types of geometries you're printing when it comes to your control over orientation. So it's hard to separate your orientation from the build direction, and in some cases you can have negative effects such as weak material properties in the Z direction, for example, with a layer by layer approach. At Fortify, we use magnetics. This happens to be a scalable technique for controlling fibers in a wide range of particle sizes. And in this case, our patented technique allows us to work with both magnetic and non-magnetic materials. And the way we go about working with, say, a glass or a carbon fiber is by treating the surface with a trace amount of magnetic material, and that allows us to control these fibers using Fluxprint. And so I've mentioned Fluxprint a few times here, and when we talk about Fluxprint, we're really referring to this process of using magnetics that surround the build volume of the 3D printing process to control for these particles during the layer by layer process. And so on the left, you see in real time, particles are aligning in a fraction of a second, and that is what allows us to control for greater thermal, mechanical, and now we're getting into even electrical properties. To break this process down, I'd like to just walk through this flow chart where we're starting with a liquid resin. And if you'd like to learn more about how we're handling these heavily filled, high viscous slurries, I'd encourage you to check out the CKM Tech Talk. But that's out of scope for this. Essentially, we have these highly homogeneous or well-mixed slurries that flow into the build volume. With Fluxprint, we're able to control the magnetic field that aligns these particles. And then in this third phase, we're programming or fixing the alignment of those materials using UV light. And this process can be rinsed and repeated so that we can not only achieve multiple orientations per layer, but we can also do a layer by layer type of peel ply that's conventional in the composite industry. Just to give you an example of what this might look like, here we have a 3 orientation build. This is 1 layer of material. This is using magnetized carbon fiber. And in the background here, this lighter gray region, we're actually orienting particles towards you through the plane so that you're actually looking down the long axis of these fibers. Whereas in the other 2 regions, you have essentially a 45 in the XY and then minus 45 on the other side, capable of doing some pretty complex orientations here. And we'll get into some of the repercussions and how this manifests in terms of improvements in mechanical properties soon. So I had mentioned that one of our key theses is that neat polymers will only take the engineering applications so far. And so on the left here, we have an off-the-shelf photopolymer. And on the right, we have that very same photopolymer that is reinforced and aligned using Fortify technology. And we're able to show a dramatic improvement in the functional properties that goes beyond just strength, but into stiffness, toughness, etc. And as Ben Arnold will get into in the Fortify product release tech talk or product presentation, we have a configurable set of Fluxprint technology that we're releasing to the market. And as I indicated earlier, particle orientation is key for mechanical properties. And so what we're displaying here is how with our Fluxprint 3D, we're able to align particles in the XYZ axis such that you're always getting optimal mechanical properties. And this is data from our Fortify DT resin, printed in the Z-axis, which is typically the weakest axis for 3D printed parts. We're still able to show really appreciable improvements over the neat resin. With our Flux Z, which is on the Flux 1 printer, you still have that ability to improve mechanical properties in the Z. However, in the X and Y, you have a slightly lower tensile strength and stiffness because particles are essentially random. And in the case of our Flux Core without Fluxprint, if you're using these types of materials, you're essentially going to have a lower strength, lower stiffness due to particle orientation. And to give you a more complex example of this, if you take a classic engineering constraint, you have a hole in a material that's going to be loaded. How would you go about reinforcing so that that hole doesn't create cracks and cause the part to fail? In this case, we've been able to show that using a Flux 3D approach where you're orienting fibers around that defect, you're able to reinforce it no matter which direction that part gets loaded. Whereas with, let's say, 1 degree of orientation, let's say that's a Flux 1, you're able to really only reinforce it in one stress state. And so the takeaway here is that you can get to much more robust parts using a Flux 3D. However, you can still reinforce for that main use case using a Flux 1. And we're starting to show how these more complex alignment patterns can lead to dramatic improvements in toughness as well. And so this is some really interesting work that was recently targeting the effect of fiber orientation on toughness of a part. And in this case, alignment here can really lead to a greater than 5x toughness difference. And therefore, how can we take this into printing robust composites? That's something that we're excited to share. In addition to programming toughness, one of the last areas I'll point towards today that also has a breakout tech talk is in the area of thermal conductivity. And so while biocomposites are primarily going to be used as inspiration for improvements in in mechanical properties, we've been able to take those same types of alignment principles and apply them to thermal conductivity as well. And so this is a new space for polymer-based 3D printing, where we're actually able to use aligned additives to hit levels of thermal conductivity that can be used for heat exchanger applications while maintaining a high level of electrical resistance. And so anytime you have something close to a high power source, that's an issue. And so that's an area we're excited to bring into heat exchangers and connectors. And again, you can learn more on the Thermal Tech Talk. And so thanks for your time. I look forward to hearing from you and hearing about how Fortify can reinforce your materials. Thanks.